everyone. In our project is EV ADAS dashboard, SMT Bluepill, and Bismillah Python dashboard simulations. In our teammates are Vivek Virabadi, Jeevan, Sanjay. And thank you for giving this opportunity to explore our knowledge. Let's go through our projects. The EV vehicle dashboard main defect is real-time data overloaded. Real-time data overload nothing but it's depends upon SOC, speed, temperature, torque. SOC is nothing but state of charge. It's called as a SOC. And disconnecting silos, safety threats. It's safety threats nothing but blind spot. We can't see any outside the car, light side, left side or right side. Using this ADAS solution used to, we can ensure our safety and reduce the hazard, avoid any hazard to lead that. These are connecting ADAS solutions to unified the co-processor, active collision prevention, risk virtualization dashboard. Unified co-processor, low cost SGMT architecture acting as a virtual vehicle controller unit. VCU to process the multiple sensor stream. Using is to we can multiple sensors are we can control it. Active collision prevention. 12 areas engine computing time to time collisions and blind spot warning under the driving condition. When we in driving ACP used to we can avoid the collisions and we can watching the blind spots inside. Risk virtualization dashboard. High speed 11,500 UART telemetry pipe directly connected to the custom MATLAB U1 interface. Go to the next slide. In our architecture is a end-to-end system architecture. Data flow life cycles depends upon sensor acquisition, ECU core and logics, serial telemetry transfer. The sensor activations are mainly for SMT ATC, potentiometers for simulations, pedals, inputs used to we can accelerator, brake and motor temperature, timer inputs capture ultrasonic echo bits, and ECU core logical, see her library. In this library used to we can physical drive formulas and monitor the temperature faults and execute the avoid ADAS alarm algorithm. Serial telemetry transport. UART is a universal asynchronous receiver and transmitter. It's a protocol we can connect the microcontrollers and sensors. It's most commonly used protocol for embedded system. Using in at 12,000 bytes every 100 minutes. Real industrial standards versus simulations. In real production EV equivalent, vehicle sensors are mainly in vehicle speed, radar, temperatures. In our simulation system implements potentiometers and HC SRO4. Mechanical hardware mapping, 12-bit data channels, total balance in port 1 to 2 plus timer input capture the triggers. VCU, ADAS, ECU controllers in real production equipment. In our simulations, SMT Bluepill F103 C8 T6. Mechanism and hardware are ARM Cortex M3 running bug metals C with SMT hard libraries are used. CAN bus automation dashboard clusters digesting of the TTC registers. In simulations, MATLAB in live. In mechanism and hardware mapping, multi-headed Python dashboard processes loading at 10 frames seconds. In diagnosis, live interactive cell allowing custom fault injections and parameter control. In these methods and simulations are used to, we can avoid the collision or accidents in real times. We can avoid the hazards.
Mapping, environmental setup, peripheral wiring, film core calculation, real-time communication, and graphical interface rendering. Next one is project roadmap, 9 development phases. First one is DEV environment, STM32Cube IDE, PCIe SimLab. Second one is GPIO and peripherals, configuring LEDs, TIM4 buzzer, PWM and active hardware interrupts. And third one is ADC sensor inputs, potentiometers mapped to accelerator, brake and motor temperature channels. Fourth one is EV dynamic model, modeling of speed, torque, SOC battery depletion, range estimation and region. Fifth one is ultrasonic ADAS, HC SRO sonar data calculation driving, FCW, DCD and active DTC warnings. Sixth one is fault and alarm system, pit field diagnosis, fault registers coupled to 4-level active alarm ratchets. And seventh one is UART deploymentary, high speed 1,50,200 bps transmitter. And eighth one is UART shell, distractive live command interrupter allowing testing and deterministic fault injection. And ninth one is Python dashboard, multi-panel dashboard visualization, live charts, speed dials and trackings. Next you see phase 1 and 2 environment peripherals, software stack, establishing a flawless co-simulation loop, STM32Cube IDE is a core development environment system clock settings and HAL configuration, PIC SimLab simulator, virtual workspace, modeling blue, PIL MCU pins, ADC arrays and COM pipes. And Python executable feeds the serial telemetry stream using into live plot windows. Next you see phase 3 and 4 ADC and physical EV dynamics, 3-channel ADC sampling, STM32 scans, analog input mapped a PA0, PA1, PA2 using 12-bit registers mapped every 100 ms. First one is PA0 accelerometer, interrupt potentiometer voltages requested, torque curve percentage 0 to 100%, PA1 brake pedal, capture brake mechanical percentage, power draw and engages regeneration logic, PA2 motor temperature, model extreme physical properties representing heat scaling between 25 degrees Celsius to 120 degrees Celsius. Next, dynamic physics modeling. The STM32 implement classic automotive motion parameter when braking at speed with pedal levels 5%. In the formula, torque region equal to minus 80 Nm into brake percentage, speed equal to integral torque by mass dt. You see active ADAS engine, distance and time to collision processing is classified into 3 types. First one is FCW, forward collision warning. Second one is TTC, time to collision. And final third one is PSW, blind spot detection. Consolidated project overflow, consolidated project workflow, comprehensive control loop, 100 ms cycle. First one is capture ADC, that is potentiometer sampled. Second one is physics loop, EV equation logged. Third one is ADAS check, calculates TTC. Fourth one is UART push, formatted frames sent. And last one is Python UI, is a plots up.
System validation and live results. Active safety matrix. Proximity escalation confirmed correct alarm escalation stage from level 0 to level 3 with responsive PWM buzzer pitch scale. Over temperature cutoff. Fault OD. Register correctly if the temperature exceeds 90 degrees Celsius instantly. Reducing motor type. Stable telemetry pipe. Continuous level 5 200 serial package streaming. Verified over multiple hours without framing a buzzer exceptions. Hardware performance. Microsecond precision TM2 input capture greatly decode HC SR04 sonar waveforms. Adaptive region. Break overrides correctly. Replenish issue battery SOC. Hardware performance. Microsecond precision. Adaptive region. Dual excitation mode. Thank you. Presented by G1 Science.